chart, the runes are the same as last time. They are posted on the test information page, so everything's on the test information page because it's the information on the test. Are there any questions that I can actually legitimately answer before the test? Any questions about that? Yes. Excellent question. So in the test, you will be given a thing that says integral of, you make something up, it's not on the test, x squared sine of x. Evaluate. Use whatever techniques you think is the most appropriate. So that is in fact a challenge in integration. Besides applying the technique, is recognizing when to use the technique. So yeah, we will not specify what technique to use. That's your test. Other question? Yes. Are we going to specify whether to use shells or washers? No. Again, same thing. Whatever you think is going to be the easiest for you to use. If both methods work, you can use either one. What was the average on this video? I don't know. I honestly have no idea. Not dramatically different, I think, from the last one. Yeah, but it's been 2 years since I've taught the course, so it's not fresh. But you guys are going to get a higher average, right? Yeah, there we go. I can feel the optimism. Any other questions about the test? Okay. Is this going to be on the test? Okay. So take a moment, sit back, relax. How was it physics yesterday? How'd it go? It's easy? Not sure that's a universal thing, but okay. That one was okay. I aspired for you to say the calculus exam was okay on Thursday. That's what I aspired for. All right. We are going to look at a topic that is not on the test, but it's going to be showing up on the final exam, as you might expect. We're going to start with approximate integration. And the classic question you get from students about this is, why would we ever want to approximate an integral when we can do it exactly with the fundamental theorem of calculus? You'd be right, we shouldn't ever settle for second best if we can avoid it. However, some integrals have no closed form antiderivative. This is the same for your 1 plus cube root of x. Could we integrate them if they were a little different? Absolutely. If someone snuck an x in front of that thing there, then we could do integration by substitution. If that was an x squared instead of an x cubed, we could use trig substitution, absolutely. But sometimes physics, chemistry, whatever, doesn't give us the integral we'd like. And this one here actually comes up all the time. I think I mentioned it earlier. This is the bell curve. This e to the negative x squared is the basis of the bell curve for normal distributions, Gaussian distributions. It shows up everywhere, and we often want to integrate it. So it's a real hassle, actually, that this has no closed form antiderivative. But it doesn't. So what do we do? Well, let's get concrete about this. What if we said, what's the integral from 0 to 2 of that function? And I forgot to plug my clicker thing. So you get your clickers out. I'll get my clicker receiver out. And meet back here in 2 minutes. So ask yourself, what are we going to get at the end of the day with this integral? 3, 2, and we're going to do ants here. There we go. All right. That's our problem in a nutshell. Wow, that was weird. We had 10 pages. All right. The integral value is perfectly well defined because we can sketch a graph of this, as did on the last page in fact, and then ask what is the area on that underneath that graph from 0 to 2. That's exactly what the integral represents. What's the area underneath the graph from the start point to the end point. And we're stuck with that no formula thing. So there is a real number that we're looking for. We just do not have a tool right now to get that real number. That's the frustration. Okay. And just be aware of that distinction. Because we can't get a formula doesn't mean the question isn't valid. It just means our technique is failing us at this moment. So what are we going to do instead? Well, what we can do is look at the common cases when this arises. So this e to the x squared is one case. Another very common scenario that arises when we need to approximate and can't use formulas is when we don't actually have a formula for the function at all. So, I was going to call my cell phone, but I forgot it today, ironically. In your cell phones, most of you, there's an accelerometer, which measures what? Acceleration, yes, that's the name. All right, so if you think of what that accelerometer can do, it can record over time your acceleration. And whatever it's doing, I think my computer here might have one in it. As we move it up and down, it measures the acceleration because it can, anyway, I won't go to technology of it, but it can measure the acceleration. Think of when you use this, if you're doing panorama shots with your phone, how does it know how fast you're moving? Well, it's measuring acceleration, and the integral of acceleration is velocity. Right, so it can tell how fast you're moving. If it wants to know your position, it can integrate again and get position. But does it have a formula for your shaky hand as you're trying to hold something over top of a cliff edge looking down? No, it doesn't. It has points that it measures, and what we're trying to do is implicitly figure out what the area underneath this acceleration graph is without knowing a formula. So all we have is data and no formula. And this happens all the time in practice. That's just one example. Anytime you've got measuring devices, stress strain, when you do material stuff, these are things that you can measure, or if you're a geotech person, you're going to measure some component, and you're going to accumulate like gravity sensors, and you do aerial surveys. There's all these things where you accumulate something that you're measuring, and there's no formula for what you're measuring. It is what it is, and you need to find the integral of it. Okay. So in fact, in most scenarios, this is the most common case in engineering. The other one's going to be one we're going to explore in this class, because it's nice to have formulas to work with, as we learn about it. Okay. All of this is to say, gee, wouldn't it be nice to have some other way to get the area under a graph besides the fundamental theorem, besides antiderivatives, because sometimes we won't be able to do that. Let's see how we can estimate these values. All right. Well, we're going to take 3 steps back and then maybe a step forward today. So we've got a graph. We've got some boundary points A and B. And we're looking for the area underneath this graph. That's our goal. Compute the area underneath the graph. Knowing that we can't use the fundamental theorem, we've done this already. How did we do this last time? Riemann sums? Yeah, what would that look like as a picture, though? What picture should we draw to go with those Riemann sums? Lots of rectangles, yes. We said, wait, we can approximate this curvy area with shapes whose area we know exactly, and that would be rectangles. And so. And 2 more. There we go. does that look like in terms of the sum? Well, this is the same kind of symbolism we've been using up till now for approximations, and we went to the integral. X sub I star delta x I equals 1 to n. N is our number of subintervals, and I, 1, 2, it's the counter, over the intervals. Or these subintervals here. So reminder of what the summation notation means again. Sum from I equals 1 to n, so I is going to equal 1, then 2, then 3, then 4, all the way up to 10, 100, however many integrals we choose to use. And then we're going to add up for each of those I values. This is a height, and this is a width. Our rectangles are going to be made up of those two dimensions, heights and widths. The heights come from the height of the function, so f of x here. And the widths are just going to be the delta x's, usually the same interval size. That's usually how we pick, but it doesn't have to be. And that xi star, I don't remember what that meant, that xi star thing. Yeah. Exactly. You had to choose a point. Remember, like choosing your favorite kid, whatever, something. You had to pick one point on the interval that you would choose to represent you. So xi star when I is 1 is some point on the first interval. Xi star is some point on the second interval. Xi2 star. Xi3 star is some point on the third interval. And what our goal is today is to maybe look at a few options for that special choice and see how well they do at evaluating the integral. Okay. So this is going to be an approximation because, of course, we're losing something. We're not going to get the exact fit of a rectangle to the curved line because the rectangles aren't curved. But we're looking at that sacrifice if it's the only tool we've got. Okay. So let's tackle this with an example where we would know the right answer, because whenever we're estimating, we should know how bad our estimate is. So let's take an example that we could work with. Let's do a quick check on this. What integration technique would work on this integral here? Show of hands for substitution. Let's go in order. Okay, show of hands for partial fractions. Okay, those would be the two big ones. Trig substitution, anybody? Substitution would be the way to go, I think, on this, because you've got something, x squared plus 1 inside, and its derivative x outside. And in fact, you will get a nice law to do that. So, as a prep for your test on Thursday, we would probably let x, w, or u, I think we call it, right? U equals x squared plus 1. So, if you believe that, and it's true, you should believe that. But you could get to 1/2 the log of 2 is the final answer of this, and that equals 0.34657. Obviously, there's a continuing decimal there, because log of 2 is a crazy irrational number. But that's good enough. You know, for engineering purposes, we probably don't need more than 4 or 5 digits on this to get something that's sufficiently accurate. So what else do we do? We can actually draw a little graph of what we have here. And we have some values. So on our x-axis and on our y-axis, or f of x, we can divide this interval. Notice the interval, 0 to 1 is a range of x values. So we're going to plot from 0 to 1. We have, by just plugging x values into this formula and getting y values back. So no complicated antiderivatives yet. No calculus yet. Just plug in values, what does the graph look like? We're going to get a series of points. I'll subdivide this here. On a nice even grid, let's say 0.25-ish, 0.4, 0.48, and 0.5. That's a rough sketch of the data points for this graph. What we implicitly want, of course, is we know that this is going to be probably a smooth looking function. It's not too exotic. So it's probably some nice curve that joins those points. And we're looking for the area underneath that graph up to x equals 1. That's our goal. Estimate the area. As always. What we said over here is that this 3.34 whatever here is the exact area. So this is an example done for educational, illustrative purposes. And we're going to work with it and try some different techniques and see how well they match up with the known right answer. So it's a good test bed. Okay. So what we're going to do is use these as our points, and we're going to try to use them in different ways to see how we can come up with different estimates of the area. Let's start off with using two intervals. So we're going to talk about this interval going from 0 to 0.5, and then to 1, f of x. And we're going to have our 4 points here, basically increasing. And what we're going to do on each interval is take the middle point, because the middle point somehow seems representative. Why take the furthest left? Why take the furthest right when we have a middle point we can pick? And if we do that, we're going to get an area built out of two rectangles using the midpoint of each of those intervals. Move that over a bit. Using the midpoint of each interval as our height. So this is our x1 star, if you like. It's our selected point on that interval. That's way too small to read, sorry. And the height there is the value of the function at that point, and the same thing here. What I'm trying to do here is tie the notation we used earlier to the picture that we're drawing here. So on this interval, we pick some representative x value, call it x1 star. It'll be the middle. We pick that. So this is a choice we make. And then we say, well, how high a rectangle would I get if I use that in my function? Well, that's what I get from my table. And then I go to the next interval and say, well, what's the height of this midpoint here? What do I get for a height of a rectangle that goes in there? Sorry, that's not a question.
Yes. I was thinking about it. I mean, we take the middle point, out of the 3 points, we take the middle points of each of the...
In this particular, yeah, so this is a choice. We could pick any point we liked. We're choosing to pick the midpoint. We'll try the left and the right in a second. That's the idea. Okay. So once you've made that decision, you realize you don't need calculus. The only reason you need calculus is to know that you're trying to evaluate an integral. But the actual calculations here are just what's the height of these rectangles. So our integral from 0 to 1 of x over x squared plus 1 dx is approximated by height 1 times width 1 plus height 2 times width 2. That's what we're getting. And in this particular case, these are all, let's actually write, I'm going to write a gory detail here. F of x2 star delta x. And that is, our midpoint here is at 0.25. Our midpoint here is at 0.75. So the height is our 0.235-ish. And that's the height. And what's the width of this interval? 0.5. Just be careful about that. There's two intervals going from 0 to 1, so each one is 0.5 wide. Okay. And then we add the second term, which is 0.48 times 0.5 as well. And then we pull out our calculator. All right. 0.23529 plus 0.48. All that times 0.5. That gets us 0.3576. Approximately. We have a number. Yay. All right. Is it a good number? it close to the right answer? That's what good would mean here.
We need to compare the side.
What's the right answer? 0.34657. 34657. The correct or exact value is 0.346. 34657. Well, it's not bad actually. We're off in the second digit, but yeah, we're off in the second digit by 0.1. So it's 5% error or something. Some kind of ballpark around there. More than 1% error. That's not bad for a real cheap and dirty calculation. This is not an insane way to go, is what this is telling us. We're getting a pretty decent approximation. Let's see what else we can do. What other alternatives we have on our toolkit if we just want to start with that table of numbers. Well, let's see what other ways we can divide this up. Well, we could take the same table and the same data points, and we could use 4 intervals. So we'll break this into 4 segments. And if we do that, each delta x is going to be what in size? 0.25. And then we can make a different choice on each interval. We can make a different choice. Actually, we can't use the midpoint anymore without going back and doing more calculations. So if we're going to use these smaller intervals and only have this data available to us, then our choice is basically the left or the right endpoints. We're going to do it with the left endpoint first, then we'll do it with the right. So our integral can be approximated by integral of x over x squared plus 1 dx is going to be approximated by height 1 width 1 plus height 2 width 2 plus height 3 width 3. And now you know why we have summation notation, because this gets really boring really fast. Okay, we get that, or in our case here, we're just going to go straight to the heights. We're going to have a rectangle here that has 0 height. That's not going to be too interesting. But then we're going to have the other 3 rectangles that build out of that. So 0 times 0.25 plus our height of the next rectangle, which is our f of x value there. That will be 0.23529. 0.25 plus 0.4 times delta x plus our 0.48 times delta x. Heights and widths, heights and widths, heights and widths. So the key thing is just knowing where that's coming from so that you can lay it out. The actual calculation is tedious. What's a time-saving thing we can do if we don't want to? Yeah. You got a 0.25 everywhere. This is why we like even-sized intervals. When you're doing the calculator work, I would just add the function values and then multiply by 0.25 at the end. Save yourself a world of grief. Do it however you like, but I think that saves you some time. So 0.23529 plus 0.4 plus 0.48 times 0.25, all of that, gives us 0.2788. Here we go. That's a little not satisfying because it's actually not that close to correct. The correct value is 0.34657. So not as close as the midpoint with 2 intervals. So even though we, in principle, have more accuracy here, we're using finer intervals, this choice of the left and the right endpoint and them not being that representative actually ends up doing us a disservice in terms of accuracy here. We get less accurate than we did in the last page. All right. You feel what we're doing here? Got a sketch, build rectangles, find some formula for the area of the rectangles, add it up, and get an approximate area. Show of hands for feeling okay about this. Okay. Fantastic. I'm going to do the right endpoint for you at home. There's no sense going through the same calculation. I'll draw the picture though. It is exactly the same data points. But on each interval, we're going to use the right-hand endpoint. So for this interval here, we're not going to use the left end of the graph. We're going to go to the right-hand side and use that data point for our interval. And so it just looks a little different. But it's the same basic principle. We're going to have 4 intervals, all of the same weight again. And on those 4 intervals, we're going to have a height, width, add them up, multiply, add them up. And we're going to get a number that's too big, as you might expect this time, because we're always using the highest point on each interval, so we're actually going to get a massive overestimate of the area. Turns out it's just about as bad as the left-hand estimate at the end of the day. Okay. So then we ask ourselves, could we do better? Could we improve a little bit more? Well, we've got a little Goldilocks scenario going on here. The left is always too small. The right is always too big. What if we mix those two? Would they be just right? Well, they'd be better anyway. So there is a technique where we average the left and the right-hand endpoints. Let me go on engage and check something here. Yeah. Okay. So one of the things we could do is average those two and see what that gets us. So let's actually do that calculation here. X over x squared plus 1. So if we were going to average things, we would take the sum that we get from the left and the sum that we get from the right. Those are both good estimates of the area. We average them by adding and dividing by 2. Now we can actually write this out a bit more nicely. So this was 0 plus 0.2359 plus 0.4 plus 0.48 times our delta x. All of this was our left. This is our delta x's, factored out. And that's half the sum. So that altogether is our left sum. And then we can add in, if we like, the right sum. It's 2359, 0.4, 0.48, and 0.5. All of that times, okay. Give me one moment here. Let's reshape this a bit. I was optimistic with my space. That's better. I know you can't do that. I apologize. There we go. So that whole thing there is our right estimate. Again, same basic shape. Delta x's times sum of function values. And this we can calculate pretty quickly. That times 0.25. We divide that by 2. And we get 0.3415 approximately. And we remember, what's our exact value? 0.34657. Hey, now we're talking. So, by combining these two not so great estimates and doing the natural thing, I think, with them, which is saying, I don't know which one's better, so we'll give them equal weight, we actually get the right answer down to 2 digits and off by just by 0.5 here. It's actually half the error that we had with the midpoint rule. So that's worth noting here. Half the error of the midpoint. So far, the midpoint was our best estimate. So half the error of the midpoint rule earlier. Okay, so we can improve things. Sorry, yes?
Does it mean that this is the most accurate method?
Does this mean this is the most accurate method? As scientists, you've seen an example of something more accurate? Does it mean it is the most? No. In fact, it will not be the most, and we will see a better one, and there is no the most. I'll tell you right now, there is no the most.
Accurate.
There's just a trade-off of effort versus accuracy.
Out of the four.
Out of the four methods, even there, not necessarily. The midpoint and the track. I can tell you what the method's called. That's next week. This rule and that rule, there's no guarantee, but they're going to be comparable. And on an individual example, one might be slightly better than the other, but they're both better than the left and the right. That one. Okay. All right. So let's throw some symbols in here just to get some practice with sums, because you're going to do lots of sums at some point in the next couple of years. So the way we typically, and again this is a standard, not something on a stone tablet or anything. This is just, we like counting from zeros when we have n intervals or n subintervals. Hold on. Is that right? If I want to use the left-hand rule, I'm going to have heights times width, that's good. But on the first interval, which x value do I use for the height? x0. First interval, I use x0. Is that what this formula is going to give me? No. So I need to tweak it somehow by doing what? This is one way to do it. Another way, of course, would be, or totally optional, I equals 0 to n minus 1 f of xi. So one way is to say, I'm going to count 1, 2, 3, 4, 5 up to n. And then I'm going to take the one less x value, x sub 0, x sub 1, and then notice the last one that I'm going to use is xn minus 1. The last one from the left-hand rule is the second last point that we have on our interval here. If it's the left-hand rule, I never do use that right-hand final xn value. Another way to write that is to start at 0, and if I count from 0 up to n minus 1, that's literally rhyming off each of those things and then stopping at the n minus 1 value and then stopping at it. Entirely up to you which way you want to write it. The right sum is actually what we had the first time. Here we just have x sub I delta x. Yeah, don't belabor this out, thank you. Again, for those who have not seen summation, this might seem a little cryptic. So if there are questions, now is a great time to ask. A lot of people have seen it, so I don't want to go into gory detail on it. Questions? Okay. Just remember you're subbing in. I equals 1, hey, f of x1 delta x would be my first term for the right sum, and that's exactly what we want. What would the next term be? X sub 2. I equals 2. And go on. Okay. The reason I put those formulas up there is because you'll see them sometimes. Let's actually give this new approach that we took a name, though. So this averaging of the left and the right actually has a nice geometric interpretation to it. If we draw this out, and this is our f of x, and this is our x, and those are our data points. And the height is 0.5 up here. The rule that is averaging the left and the right turns out to be the same as if we drew little trapezoids. And Broker intervals like this. And you can see, I hope, that this is going to more closely resemble some nice smooth curve through that interval because, well, I'm not using horizontal lines all the time. Now I've actually got lines with some kind of slope that can better approximate the function itself. So I'm not limited by rectangles, I'm actually using a more complicated shape here. And that gives us a payoff. Doing that gives us a more accurate estimate because it's more closely representing the actual shape of the function. So that's awesome. The question is, how do you get this formula? Well, if you wanted to start here and say, well, this is a reasonable way to tackle the area question. How can I find the area on each of these rectangles? There's a couple ways you can do it. One is to, okay. So one is to look into your trapezoid. We're going to exaggerate the extreme part here, the nonlinear part. Let's call this f of x1 here. That's that height. And this height here is f of x2. Just out of curiosity, how many people know a formula for trapezoid areas off the top of your head? Okay, like 5 people. All right, so it's worth going through this. This is good. All right, and delta x here at the bottom. A trapezoid is made of a rectangle and a triangle. We know the area of each of those shapes. Rectangle, the total area is going to equal the rectangle plus the triangle. The rectangle's area is f of x1 times delta x. The triangle area is 1/2 of, what's the height of the triangle? You have to subtract, right? But f of x2 is this whole thing, but I don't want this part. So this height over here is f of x2 minus f of x1. It might sound a little weird, given where we're going with this, but we're going to follow along. So the height is that minus that times delta x2. Delta x. That would be the area of the rectangle and the triangle added together. And we can tidy this up a little bit though. Because we have an fx1 there minus a 1/2 x f of x1. What does that give us in the end? Let's read it down here. That gives us f of x1. How many of those? Half of those, yeah. Plus a 1/2 of f of x2. All of that times delta x. And that's much more commonly written as this. Hey, there's our average of the left-hand point and the right-hand point. It is not a coincidence. If we were to draw trapezoids, it would have the same effect or end up in the same area as if we had averaged the height of the left and the height of the right. Okay. Just for fun, we should see why that's true. Okay, so let's pick this interval here. If I average the heights between them, and I make a rectangle there, how do I know that rectangle is the same area as the green trapezoid? Things cancel out, exactly. If I cut this part out here and move it on top of here, it's perfectly symmetric. That little triangle flipped around is going to cover the same thing because I picked the midpoint halfway up this trapezoid. So that's another way to look at the average of the two heights. So halfway, the y value halfway between the top and the bottom, giving us the same area as the trapezoid. The trapezoid looks greener, but you can see that there's some connection between that and averaging heights in the shape. Does this really matter? Oops, sorry. Give me 1 second. Give me 2 seconds. There's cables everywhere here. There we go. Let's try that again. So the reason these matter is because they have a source, and it's easier to memorize things when you know why they are what they are. If you like, you can just go memorize this. That's a perfectly valid alternative. What do we get if we generalize this into a formula? We get exactly, sorry, over 2, exactly what we'd expect when we take that formula and apply it to each interval 1 by 1 by 1. We have the left-hand rule, which we said was I minus 1 for starting at I. The right-hand endpoint, which is xi, we're starting at 1. Take the average of those, multiply by height or by width, and we get areas of trapezoids that are a good representation of the overall area. Okay. That's the trapezoidal rule. Let me just check page. Yes. Okay. It's the same. It's worth knowing that there's a shortcut for the trapezoidal rule as well. If you regroup things, sorry, let me do this. Yeah, over right here. When you're calculating these things longhand, honestly, I'd always use a computer for this if I had a choice, but under exam you won't have a choice. So it's good to have a strategy that will get you through this as quickly and efficiently as possible. If you look at what we're going to calculate and look at the factors that you can pull out in common, let's do the first 3 terms here. Not first 2 terms. Over 2 plus. What you'll start seeing if you write it out longhand is there's some patterns. So first of all, you have a delta x as a common factor. Every single term has a delta x. In fact, it actually has a delta x over 2 as a common factor. Every single thing has this 2 and a delta x. 2 and a delta x. 2 and a delta x. So we can pull that out. Then what you notice is some of these values repeat themselves. My first value, f of x0, only gets used once. It's the left-hand rule part of the first interval. But every other one appears twice. The end of the first interval is also the start of the second interval. The end of the second interval is also the start of the third. The end of the third is the start of the fourth, and so on, up until the last term, which has the n minus 1 and xn over 2 delta x, has the same common factor. The last value would be paired with something earlier, but this one here is going to be all by its lonesome. So this one, so goes, and so is this one. Everything else, all the other values will come in pairs. And to sort out what that would mean, well, if I add those up, I'm going to have 1 of the first value, 2 of the second, 2 of the third, 2 of the fourth, 2 of the fifth, 2 of the ninth, and the last one's my 10th, I'll have 1 of it. So it's just a 1, 2, 2, 2, 2, 2, 2, 2, 1 multipliers is one way to write out the sum in a way that's fast to calculate with a calculator. Takes care of all the common operations of dividing by 2 and multiplying by delta x. All right. So you said you should memorize. It's probably a good idea to memorize this because it's faster than its equivalent. This is just as good. This has all the same information, but it's a little less calculator friendly. It would make you do more manual labor to do that term by term by term. Okay. I think we do have time for the last one. It makes a nice wrap up. Oh no. Okay, we'll do the estimate here. We'll save the last method for tomorrow. So one thing as engineers, if you have error, you should probably know how big the error is, right? I've got an estimate. Is it off by 100% or by 1%? That makes a bit of a difference in terms of the analysis and in terms of what you're going to trust in your analysis. So let's take a look at a classic integral where you have a formula. So we have the formula here. And we say we're going to use the trapezoidal rule because up to some debate about it in the midpoint, the trapezoidal certainly seems one of the best. What would be the other decision now you'd have to make? So I'm going to use the trapezoidal rule to estimate this integral. I've got some picture of it. One looks like a cube. I don't know, it looks like something like that. I know I want to estimate that area. Before I can do that, what do I have to choose, decide?
Yeah.
Your delta x, exactly. You need to pick delta x, or, if you like, the number of intervals n. Okay. Then you might ask, well, I'm willing... Oh, wait. What's the trade-off we're explicitly or implicitly doing here? Higher n equals more work. Right? If I have more terms, I have to do more calculator pressing. If I'm a computer, I still have to do more loops through something. It'll take marginally longer. So using a bigger number takes more work. So what's the trade-off? How much benefit do I get from that? Well, it turns out there's a really nice way to put a bound on an error. So this is our error down here. Error in our integral estimate. And there's a few factors. Now, one of them, not surprisingly at all, is the length of our interval. Overall interval. Okay. B minus A is how far is it from the upper end to the lower end? Well, if I am doing my estimate over, think of this geometric idea, over 1 meter or 1 second, there's only so much error I can build up. If I do it over a year, then my errors are going to build up more and more and more. So it's not too surprising that this thing, the bigger it gets, the more error. So larger intervals, larger error. Larger interval. And we can't change that. That's what we're given in the problem. This is the overall interval, not the ones that we pick. Larger error. Where do we get to pick? That's our n down here. N is the thing we control, which is our choice on the number of subintervals. Our choice of the number of subintervals. And so far we have nothing to do with the function yet. I could be integrating anything, and these factors would still show up. Where does the actual shape of our function come in? This little k value here. This k is an upper bound on the second derivative, which is the concavity, or the curvature. The max curvature of f of x on our interval AB. So we get some feeling from this about what things matter in terms of getting a high accuracy. So we want small error. We want small error. That's our goal. If we make n bigger and bigger, we get smaller and smaller error. So that's our more work, gives us more accuracy to the thing, which is nice. We can't control the length of the interval. That's however long we have to integrate over for our problem. And we also can't really control this because this is whatever our function is. But we get some sense that the more curved it is, the worse the trapezoidal rule will do. Let's see why that might be. So the more curved it is, the worse the trapezoidal rule does. Well, let's pick a function that maybe looks the same here. Has 2 endpoints that look the same. We'll do the trapezoidal rule estimate on it. And we'll compare 2 different curvatures. This. Which curve has the highest second derivative value? The left or the right? Right. This second derivative is larger here. More curved. When we get to vector calculus, we'll be able to define that more precisely. But this is more curved. This is smaller. And so f is closer to linear. Well, and that means that f is closer to the shape of the trapezoid. look at our straight line. If second derivative is 0, you actually have a straight line. So as our second derivative is small, then our trapezoid approximation is great. If our function is curving all over the place, then straight lines are fine, but they're not a good approximation of the actual shape of our function. So we get more error, and that's exactly what we see down in this rule here. The more curved it is, the less well our trapezoid approximates it, and we will stop there for today. Thank you very much. See you tomorrow morning, right early at 4:30.